Okay, yeah, we're very happy to have Kevin Zhang. He's got his PhD in 2012 from at Michigan, and then went to Daisy and Berkeley and is now at Caltech. And he is going to tell us about the effective field theory of dark matter with collective detection with collective excitations.
Cool, thank you, Marcus, for the nice introduction, and thanks a lot for the invitation. It's my great pleasure to be here with the group. Today I'm going to talk about my recent work in collaboration with Catherine Zurek, Caltech, and her student Tanner Trickle, the effective field theory of dark matter direct detection with collective excitations. So one technical question, it seems the highlighted video is Marcus's video, not mine. Is there a way to change that?
It's at your end. So
it's yours.
On our end, when you're talking, you're the highlighted video.
Oh, okay, cool. I see. So it's just I can't see myself. It's okay. I'll just.
I think that's in your settings. You have to click.
Oh, that's in my, okay.
To see yourself when you're speaking.
I see. Thanks. All right, let's move on. Speaking of direct detection, perhaps the first thing to come to mind is a plot like this. Conventionally, searches for dark matter were heavily focused on weakly interacting massive particles. So we have been making a lot of progress in detecting or really excluding weak scale mass dark matter. And these are based on nuclear recoils, and we see that all these curves, they turn up at around the GeV. So we don't have sensitivity for dark matter masses below a GeV. And the reason is quite intuitive to understand. Suppose we have a weak scale dark matter at 100 GeV. When it hits a nucleus, say a xenon nucleus that has a similar mass, we can try to detect a recoil signal. But if the dark matter is much lighter, below a GeV, it's hitting a much heavier nucleus, so it just bounces back, and the heavy nucleus barely moves, and then we can't detect a recoil signal. But of course, one way to go beyond that is to realize that there are also the much lighter electrons in the target. So instead of just interacting with the nucleus, we can imagine the dark matter coming in and knocking out an electron. So this kind of atomic ionization process has the typical energy scales of order 10 electron volts. So of course you can recall from elementary quantum mechanics that the binding energy of a hydrogen atom is 13.6 eV. And for heavier atoms, for the outer shell electrons, the numbers are not very different. And a related set of ideas to use semiconductors, basically when we put atoms together in a crystal, we're not looking at the individual atomic orbitals, but rather the electrons when we see them in momentum space form band structures. And in the ground state at zero temperature, there are these valence bands that are filled, and above a band gap of order electron volts, there are conduction bands that are empty. So when the dark matter comes in, it can trigger an electron transition from a valence band to a conduction band, and then we can try to detect the associated scintillation or ionization signals. So this set of ideas has been extensively studied in the past 10 years or so, including by myself. And there are already experiments that are ongoing, super CDMS and Scientific, that utilize this idea. So with sensitivity to order electron volts energy deposition, we can reach down to dark matter masses of order MeV. So remember that the kinetic energy is about 6 orders of magnitude below the dark matter mass. But again, we can ask the same question: what if we want to detect even lighter dark matter? For dark matter lighter than about an MeV, it doesn't carry enough energy to trigger an electron transition of order eV. So we can't use electron excitations for direct detection. But of course, I should mention that there are some targets with much smaller band gaps, order milli-eV, that have been proposed, including superconductors and Dirac materials, but these are somewhat futuristic in terms of experimental prospects. So we like to look for something that's more readily available for experimental realization. So this is what brought us to consider collective excitations. And perhaps the most familiar type of collective excitations are phonons in crystals. So these are collective oscillation modes of the ions at sub-eV energies. And the cartoon picture is that when the dark matter comes in, it interacts with the crystal lattice and excite one of these collective excitation modes. So this is something that has been proposed more recently and has been studied by people, including myself and other people in Catherine's group. And we have computed the theoretical sensitivity for a variety of materials using single phonon excitation. And this is what the result looks like. If I just patch our reach plot together with what you saw on the previous slides, we see that for dark matter nucleon interactions, we can extend the reach to a lot below a GeV, down to about 10 keV in this case. And we can cover a lot of the parameter space above the neutrino floor. So that's the theoretical part. On the experimental side, there were also some good news. The Tesseract dark matter project, which is based in Berkeley Lab, is funded and is in active R&D at this moment. There is a sub-experiment that use a sapphire target and a gallium arsenide target to look for single phonon excitations. And they're designing ultra low threshold transition edge sensors for phonon detection. Beyond phonons, we can of course also think about other types of collective excitations because I mean, the condensed matter physics is a vast field and there are really a lot we can look into. And beyond phonons, we have, for example, looked into magnons. So these are collective spin excitations in magnetically ordered materials. And the cartoon picture is that in the crystal target, this is showing a ferromagnet where all the ionic spins are aligned in the ground state. And when the dark matter comes in, if it couples to these ionic spins, you can trigger one of these spin excitation modes or a spin wave in the classical picture. So this is something that we proposed back in 2019. And so this similar set of ideas have also been considered in the context of axion detection. And although experimentally, this is not something that's very close to realization yet in this current context, there is an ongoing experiment called QUACS that is somewhat similar that look for axion-induced magnon excitations. All right, so up to this point, all I have been showing is a two-dimensional parameter space of interaction strength or cross-section versus the dark matter mass. And I've been showing plots like this, but we can imagine that there should be a third axis of the parameter space in a very abstract way. Let's call it interaction type. So basically, this is just showing a particular model or a particular slice of this parameter space. And here I'm assuming that there is a heavy scalar mediator that couples to nucleon number. So this is the case that matches onto the nuclear recoil sensitivity plot. And for example, we can look into another benchmark model that's often considered, which is the dark photon mediated scattering, where the dark photon mixes kinetically with the standard model photon. And here, the sensitivity curves look very different, and the question of which materials do better also has a different answer. Of course, we can imagine there are infinite slices, infinite number of slices in this parameter space corresponding to different dark matter models. And we want to study all of them. But in fact, this is the picture that we run into. There are just so many possibilities. So the way forward would be to find a common description at low energy that's appropriate for computing direct detection rates. And obviously, such a framework is provided by effective field theory. So starting from a broad class of dark matter models, we can derive a non-relativistic effective field theory of dark matter standard model interactions. And the set of operators is already well known, and I'm listing them here. And starting from these operators, we can basically forget about the UV models and just compute how the dark matter interacts with the crystal target starting from these operators. And that's what we call crystal responses, basically how the dark matter couples to the lattice degrees of freedom. And very intuitively, we can imagine that the lattice degrees of freedom that the dark matter can couple to would include the particle number, how many protons, neutrons, electrons there are in each ion, the total spin, orbital angular momentum, and spin orbit coupling. And in fact, these are exactly the quantities that will show up in the EFD expansion at leading order, as I will show very soon. And finally, starting from these dark matter crystal couplings, we can put in the material specific input to compute the phonon and magnon excitation rates. So this is a 3-step procedure, and explaining these steps will constitute the main part of this talk. And before moving on, let me mention that this might have reminded you of something, and indeed, for nuclear recoils, there is a very similar story. Of course, at the beginning, much of the focus was on the standard SI and SD interactions, but later on in 2012, starting with this pioneering work by Dan Fitzpatrick and others, we learned how to generalize the calculation to the full effective field theory, basically starting from the full set of leading order non-relativistic operators, we can compute, in that case, nuclear responses, and then the rates. So here is a very similar story, except that we're computing crystal responses instead of nuclear responses. So as we move on, it's useful to keep this analogy in mind. So I'll start with the first part. And by the way, feel free to interrupt if you have any questions. All right, so the first part is to build the non-relativistic effective field theory. And as in any EFT applications, there is a top-down point of view and there is a bottom-up point of view. And from the bottom-up point of view, the question is, what are the building blocks involving the IR degrees of freedom? So obviously, in the present case, we have the spins of the dark matter and the standard model particle, which can be a proton, neutron, or electron. And we have the momenta carried by these particles. There are 2 constraints on these 4 momenta. First, we have momentum conservation, which is obvious, and also Galilean invariance, which the effective operators must respect, means that the operators would only involve the relative velocities, but not the absolute velocities. So taking into account these 2 constraints, we are left with just 2 independent kinematic variables, and these are typically chosen to be the momentum transfer, here denoted by Q, defined as the momentum transfer from the dark matter to the standard model target. And the other variable is called V-perp. This is the component of the relative velocity that's perpendicular to the momentum transfer. So these are the quantities that we'll use to build up the effective operators. And the enumeration of operators at leading order is a solved problem in the studies of nuclear recoils. So I'm just repeating the results here. But conveniently, we can organize these operators into 4 categories, depending on whether they involve the spin of the standard model particle, can be coupling to charge or coupling to spin, and also whether the operator involved the relative velocity V-perp. So this classification is useful because operators in the same category will end up inducing the same types of crystal responses. And I'll talk more about this classification later.
So just, sorry, can I just make sure I understand? So
yeah,
can you just go back to that? So for example, the identity operator would mean for say for the interaction with protons, it means that it couples to the scalar density PP bar, or what does that mean?
Yeah.
Is that
yeah,
right?
That's what it means. Yeah.
Yeah. And these other ones, they couple to the chorus, because these things are sort of currents. It's implicit that these are coupling to some bilinear of either protons, neutrons, or electrons.
Yeah, exactly. So
Okay.
I guess that's the equation that I'm going to show in a couple of slides. I probably should have put it earlier. So what these operators mean exactly? So these are the 4 fermion part of the non-relativistic EFT.
Yeah.
So that's the operator in between.
So maybe you'll talk about this later, but obviously there's a big difference between electrons and protons, especially when you get to the crystal response. But you really need them both. It's not that somehow only electrons matter because you're at low energies or something.
Good. Yeah. So generically, we consider both. Well, actually, all 3 types of constituent particles: protons, neutrons, and electrons, and that's what the label psi stands for. So we can have psi equals P or N or E. And depending on the precise type of excitation we're looking at, it could be that only some of them are relevant.
Okay. Well, go ahead then. Go ahead.
Yeah, so I guess what I said at this point is a little bit abstract, but I'll try to make these statements more explicit as we move on. All right, thanks for the question. There is also the top-down point of view. Namely, we start from a UV theory and derive the non-relativistic EFT by taking the appropriate limit. And for example, a spin 1/2 fermion field will have the standard expansion in terms of the non-relativistic fields, and we can just enumerate the types of couplings in the relativistic theory as shown in this table. For example, if we consider a class of models where there is a T-channel mediator exchange, if the mediator is a scalar, it can couple to the scalar current or a pseudo-scalar current. If the mediator is a vector, there is a vector current and axial vector current that it can couple to at their normalizable level. But beyond that, we can also write down higher dimensional operators, including the electric dipole and magnetic dipole at dimension 5. And dimension 6, there is an additional type of coupling called the antipole. In each case, we can derive the non-relativistic limit, and that's listed in the last column of this table. And we see that the non-relativistic EFT building blocks, the spins and momentum transfer and relative velocities, they naturally emerge from this exercise. And in the end, once we write the effective theory in terms of these non-relativistic fields, these effective operators would just appear as the operator that act on these. This will just be the part of the 4 fermion interaction. So that basically answers Marcus's question in more detail. This is what we mean by these operators. So to give you a set of more concrete examples, let's consider a dark photon mediator. So on the standard model side, it couples to the electromagnetic current via kinetic mixing. On the dark matter side, there are several possibilities. First of all, it can couple to the charge of the dark matter. Basically, the dark matter is charged under this mediator. And in this case, it's just the standard spin-independent interaction O1 that's generated. And I'm writing here the effective coupling, which takes into account screening in the dielectric medium. But that's not the only possibility. We can as well consider a dark matter that's neutral under this dark photon, but rather couples non-minimally via an electric dipole moment. And this is the operator that we write down in the relativistic theory. And once we do the matching calculation, we see that it's a different operator, O11, that's generated in the EFT. And similarly, we can consider magnetic dipole dark matter. And here, more operators are generated in the EFT. There are 4 of them at leading order. And also, some of them would involve some effective couplings where the E-medium screening is taken into account. And finally, we consider an antipole dark matter model. And here, is yet a different set of non-relativistic operators that are generated.
Did you consider the case where the dark particle has a magnetic charge coupling to the dark photon?
Ah, yeah, that would be interesting. So we didn't consider that.
Okay.
Cool. All right, so I'll have more to say on these models later on. So that brings me to the end of the first part. We have derived the non-relativistic EFT from the UV theory, a relativistic theory of dark matter. So now let me move on to the second part. From now on, we're going to forget about the concrete UV theories and just work with these effective operators. So what I've been showing you is the interaction between the dark matter and a standard model particle, proton, neutron, or electron. But there is a further step of matching that has to be done because we really have to put these particles into a crystal. So what happens is the dark matter scatters off a crystal target and excites, and it mediates a transition from an initial state to a final state in the crystal lattice. And the way to deal with this is to first write down the Fermi's golden rule, where the operator in between is the Fourier transform of the lattice potential and generally can depend on the velocity. So it's a non-static potential. And in the delta function, there's this quantity called omega q that's defined as the energy difference. So this imposes energy conservation. For a periodic lattice, we can imagine that the scattering potential takes the form of the sum over the contributions from all the ions in the crystal. And here, L labels the primitive cells, which are the repeating units in the crystal lattice. And then inside each cell, we have labeled J for the ions.
Sorry,
and similarly, sorry, go ahead.
Sorry, I'm a little bit slow here. So what is is there a physical picture underlying these formulas that's saying that you have a bunch of independent particles that are each bound in some potential? Is that the physical picture you're using here?
Yeah, basically, yeah. So we are assuming that the scattering potential between the dark matter and the entire crystal can be written as a sum in this way. So yeah.
Right. So it's kind of the physical picture is that you have a bunch of the standard model scatters, electrons or whatever, and they're at some position, fixed positions, right? And then your dark matter comes through and you're doing a kind of Boltzmann type calculation where you basically are summing the effects of individual scatters from each standard model particle. Is that correct?
That's only at the potential level, but not at the matrix element squared level. Because to get these collective excitations, we actually add up the contributions from all the scatterers at the amplitude.
Right, and you add up because if I look at your formula, you're summing over F, right? Well, let's see. You're summing over your integral over Q that's the integral over the positions of the scatterers effectively, and then you're calculating you're taking the probability and averaging it over that, right?
So you mean this integral over Q?
Yeah.
Oh, Q is the momentum transfer. So this is just the phase space integral. Or I guess it's
inside his amplitude, he has a sum over all
right. There's the
atoms,
sum.
and then he has the sum over final states.
Okay, so it is coherent. Okay, so it is coherent. So I see, right. So you're saying that you're coherently scattering off of this whole lattice, right? And then you're just calculating, but each of these potentials, you are assuming that each standard model particle is initially at some fixed position. And then they provide some scattering potential for your dark matter that's given by this V here, and then you're
Yeah,
doing
so
potential
actually,
scattering.
right. So these
Yeah.
are not fixed though. So because there is an equilibrium position, but of course,
Yeah, well,
the particles
they can
move around it.
recoil, but they initially have some fixed position. Is that right?
I'm not sure what you mean by fixed position, actually. Um, for example, if you excite phonons, you'll have to move things around, right? So,
Right,
I mean, there's
right,
an equilibrium position that's fixed, of course, but you're
right.
really making
But
excitation on top of that.
initially they have some, I guess at least they have some wave functions,
Oh,
right?
sorry. You mean in the initial state?
In the initial
Yeah,
state,
yeah. Yeah.
they have
Then there
fixed,
are, yeah,
they
there are
have
wave
fixed
functions.
positions. Okay, so yeah, so initially they have some fixed positions, and then you scatter, and then you have look for the probability to go to some final state. Okay,
Well, I guess it's see,
It has a wave
not
function
exactly fixed
positions in
positions
I,
because
in the initial state I has a wave function for the.
yeah. So it's a fixed wave
right,
function. Yeah.
okay, all right, okay,
Okay. Yeah. Thanks for the questions. And yeah, so we're writing the total potential as a sum over the ions, and correspondingly in momentum space, there's also a sum where there's a phase factor associated with each ion. And the key quantity now really becomes this V tilde Lj, which is the scattering potential between the dark matter and an ion at the site Lj. So we can compute this quantity in the EFT with these operators. And I'm going to show you how the calculation works by picking just one operator from each category because the calculation is completely analogous for the other operators. So for all of them, there has to be a sum over the constituent particles that's labeled by alpha because we're basically putting the protons, neutrons, and electrons into the ion. And of course, there is a phase factor associated with each constituent particle. And the simplifying part of this EFT formulation is that if we're looking at light dark matter lighter than about 10 MeV, the momentum transfer is always small compared to the inverse ionic radius. So we can expand these phase factors and just keep the first non-vanishing piece. So for two of these operators, or two of the categories of operators, we can simply set these phase factors to 1. So these are the velocity independent operators. And in the end, we just sum up either 1 or the spin to get the total particle number or the total spin. For the other operators, because there is the velocity operator in this matrix element, it's a little bit more involved. We first write out the velocity V perp defined with respect to each constituent particle into these pieces, and the first two terms are independent of the constituent wave function, so they can be pulled out of the matrix element. So again, just as before, we can set these phase factors to 1, and we get the total particle number and the total spin. The second piece, however, acts on the wave functions, so they cannot be pulled out. And in fact, the first order piece will vanish because of probability conservation. And we have to go to the next order to set this phase factor to iq.x alpha. And what comes out is an orbital angular momentum operator. So this can be derived after some algebra I'm omitting here. But intuitively, because once you have a position and a momentum, they have to combine into an orbital angular momentum. So to write down the full results, once we separate the velocity into those pieces, for each operator, there has to be a term that's proportional to either the particle number or the spin. And there is a second piece that involves the orbital angular momentum. So we can carry out the same exercise for all the operators, and the final results is in this equation here. So this brings me back to the classification of the operators into the 4 categories. And for the crystal degrees of freedom that the dark matter couples to, we call them crystal responses because they play a very similar role as nuclear responses in the nuclear recoil calculation. And we talk about point-like versus composite responses, depending on whether the crystal degree of freedom involve the internal motion of the constituent particles of an ion. So if the dark matter couples to the particle number or the spin, these are the quantities defined for the ion as a whole. So these are point-like responses. And we see that each operator will generate one of these point-like responses, depending on whether it's coupling to charge or coupling to spin.
Sorry, can I interrupt? I'm sorry to interrupt, but can I ask again? So another question. So for protons and neutrons, obviously they're in nuclei, right? But you're talking about just protons and neutrons. So I'm a little confused. This potential, somehow you're going to have to convolve it with nuclear structure, or what? What can you explain what's going on?
So you just get the total proton number, neutron number, for example, in the nucleus, or the total spin. If it's polarized, if it's not polarized, you get 0.
Okay, so you are really talking about neutrons and sorry, nuclei. You're talking about nuclei, but the point is that in these approximations, it's just coupling to some quantum numbers that you can just sum over. You can just find by summing over the protons and neutrons in each nucleus.
Yeah, right. The key is that we're taking the long wavelength limit.
Right.
So it's really the macroscopic quantities of the ion. We're not even talking about the nuclei, but the important quantity is the ion. So how many protons are contained in the ion? I mean, which is the same as how many protons are contained in the nucleus.
Right, so I see, right. Your momentum transfer is so small that even the electrons don't recoil individually. It's the entire ion is recoiling.
Yeah, that's right.
Because you're even below that. I'm sorry, I think you said that, but I didn't realize that. Okay, thank you.
Yeah, thanks. So yeah, I was talking about point-like versus composite responses, and each operator will induce one of the point-like responses, and for those operators that involve the relative velocity, they also induce composite responses, either L or the spin-orbit coupling. And this is because once you couple to the velocity, you're sensitive to the internal motions of these constituent particles. So that completes the second step of the calculation. And finally, I'll move on to the third step, computing the rates. So from now on, we're not going to make any more EFT expansions. We're just do the full calculation. I mean, in special cases, like at very low energies, where you're only looking at the Goldstone modes, you can as well build an EFT for that case. But we're interested in all of the phonon or magnon modes. So we're not doing any more EFT expansion. We're just doing the full numerical calculation. So because it's a full numerical calculation, it involves a lot of technical details of the material properties. So let me try to focus on the big picture to at least give you an idea of how this calculation is done. So there are 4 types of crystal responses at leading order that I just talked about in the previous part. The first thing to notice is that all of them can in principle excite phonons. And this is basically because any coupling can shake the lattice. But an important point is that it needs to be, the coupling needs to be coherent in the sense to excite phonons. For example, if it couples to the scalar quantities, say the particle number or L dot S, so these are trivially coherent because how many protons are contained in one ion in one primitive cell would be the same as the number of protons in the other primitive cell. But some of these quantities may not be coherent because these are vector or tensor quantities. For example, if you couple to the spin, of protons, neutrons, or electrons, the coupling would not be coherent if you have an unpolarized target, because the spin would point in one direction in one primitive cell and in a different direction in the next cell. So the contributions don't add up. So by to require it to be coherent, we have to have an ordered spin or angular momentum. This can be done either spontaneously, say if we have some ordering of, well, say ferromagnetic order, or by applying an external field to align the spins.
Sorry, you said that there that L dot S is obviously it's a scalar, but is it really obvious that it's coherent in a material? Maybe that's not important, but I just,
yeah, I mean,
I wonder if I'm missing something.
Yeah, coherent only means that the coupling is the same between one cell and another cell. If it's the same type of ion, and L dot S is basically a scalar charge. It's just like the particle number.
I'm just imagining that somehow L and S are just both randomly distributed, that is independently. That can't happen?
So the thing is, this is L dot S expectation value instead of the dot product of the expectation values. So generically, we don't have the spins or the orbital.
Unless if it could be, so it would be 0 in my example. Yeah.
I mean, L dot S is part of what's causing the fine structure splitting, right? I mean, it's always there, and it's larger for larger atoms.
Yeah, I guess it's always coherent. It could be 0, right?
It could be 0, but it's generically not 0.
Okay, I got it. Thanks.
Cool. Yeah. So for magnons, as I said, because these involve the magnetic ions spins, we have to couple to these ion spins. The question is what these ionic spins are. So in most cases, in all cases, the ionic spins come from electrons. The nucleons are just too heavy to contribute. And in many cases, these are just the total spin of the electrons. And in more exotic cases, the magnetic ion spins can also involve the orbital components of the electron. So the upshot of the calculation is the following. We start with the dark matter ion scattering potential that we derived in the previous step and insert it between the ground state, which we assume is the vacuum state, no excitations, and a one particle state, a single phonon or a single magnon, and sum over, well, later we'll sum over all these final states. So for now, we're just looking at one of them. So for phonons, since they come from the lattice displacements, we have to find the dependence of the lattice displacements of this operator. And the leading order dependence only comes from this exponential factor. So we're just expanding these position operators around the equilibrium positions and just write it in the standard way to obtain the phonon creation and annihilation operators. And then the question is, how do you compute the quantities that are involved in this equation? So first of all, we compute the crystal Hamiltonian by density functional theory tools. And this is done mostly in collaboration with Sinead Griffin's group at Berkeley Lab. And there are also some online databases where people have uploaded their DFT calculations. And afterward, we can use that as input to solve for the eigenvalues omega and eigenvectors epsilon. And this is just an eigensystem problem. And we use the Phonon program, which is an open source program for that calculation. So with all these technical tools, we can get all the quantities involved in this equation. And once we plug it in, and after some algebra, we derive the rate formula, which I show over here. So first of all, there is this last factor that contains the dark matter couplings. So this is the same as what you see on in the background, the effective potential but I'm removing the L label because I'm requiring the coupling to be coherent across the entire lattice. So the coupling, the potential wouldn't depend on which cell you're looking at, but only depend on which type of ion you're coupling to. And to get the total rate, we sum over the phonon branches labeled by nu, and for each branch, we sum over the individual ion amplitudes. So that's the coherent part. And of course, the phonon eigenenergies and eigenvalues appear in the expected places. And finally, I should mention that the denominator is reminiscent of a harmonic oscillator, which is quite expected because the phonon is basically a collection of oscillators.
Sorry, what's a phonon branch?
Oh, good. So I should have put a phonon dispersion here. So basically, if you plot if you find the eigensystem, the eigenmodes, each of them would be labeled by a branch nu and a momentum k. So the branch basically tells you like how many degrees of freedom there are. So if it's a monotonic crystal, there's just one branch. So there are 3 branches because each atom can move in 3 directions. If it's diatomic, there are 6 branches. So this is why it runs from 1 to 3n, where n is the number of ions per primitive cell.
So somehow each one has 3 easy axes or something, like in a cubic lattice. You either sort of move one way or this way or that way. Is that the idea?
And I mean, for any lattice, that will be, yeah, that's the idea, and that's true for any lattice. It's just that we're finding the eigenmodes. The eigenmodes won't be like moving in one direction or the other because it will depend on the weight number also, and also on the detailed crystal structure, but the number of degrees of freedom is the same.
Okay.
Yeah. So, yeah, I guess to make it more precise, imagine you have a crystal with many cells, and in each cell there are n ions. Each ion can move in all 3 directions. So 3n is the number of branches, and then you also have to sum over the k points. That corresponds to the number of cells, which goes to infinity, and that's where you take the continuum limit and becomes an integral.
Okay, why don't you go on? Because I don't want to stop you. I don't totally understand, but it's probably just me. So why don't you go on?
Oh yeah, sure. Thanks for the question. Yeah, let me move on to the case of magnons. So as I said, these have to involve the couplings to the ionic spins, and they have to come from the electron spins or orbital angular momentum. So just single out these terms in this equation. And the question is how to relate these quantities that the dark matter couples to at the particle level to the ionic spins. So this would involve the concrete understanding of what the magnetic order is and how it is formed and what the effective Hilbert space is. And that's material specific, but in the end, in all cases, we can always do a projection of these particle level spin operators onto the subspace of the ionic spins. So it will just be a proportionality constant that's relevant in this calculation. And once we get the ionic spins, we expand them around the ground state using the Huston-Primakov transformation. So these A dagger and A, these are creation and annihilation operators for bosonic degrees of freedom. And from there, we can derive the Hamiltonian for these Huston-Primakov bosons. And again, we can get the lattice spin Hamiltonian, purely derived from experiment or DFT calculations, and then solve the eigensystem to find the canonical magnon modes.
Sorry, magnons are the same thing as spin waves or not?
Yes, magnons are quantized spin waves. Yeah.
Quantized spin waves. And I think the phonon thing, I think I understand. If you have sort of different sublattices made of different species. That's what your branches are. Is that right? Like if I have,
yeah, so it can be different species or simply because
Yeah.
the crystal environments are different.
yeah, like AB, 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 then
Yeah,
A
yeah.
and B would have their own phonons. That makes sense. I'm sorry. Yeah. Okay, thanks.
Yeah, sure. So the rate formula is similar to the phonon case. Again, there is a factor that contains dark matter physics. These are the coefficients of the SE and LE in this equation in the background. And the rest of the formula, again, we have a sum over branches. For each branch, there is a sum over individual ion amplitudes. And there are these U and V matrices that are rotation matrices to magnon eigenmodes, and these are similar to the phonon eigenvectors. And finally, there has to be a vector that captures the magnetic order. So I've quickly gone over the third part of the calculation. Now we have a complete story. So in the last part of the talk, I'm gonna return to the example of dark photon mediated models and show you how to carry out this calculation all the way till the end to get the rate and projected reach. So the first step of the calculation was already worked out earlier in the talk. We have the coefficients of the effective operators for each model. For the first two models, Miller charged and electric dipole, we see that it's only the coupling to the total particle number n that's generated. Well, this is the second step of the calculation. These are the terms that are singled out in each of these models. And this response can be probed by phonon excitations. And also notice that the electric dipole model is higher order in the momentum transfer, which is basically the EFT power counting, than the spin independent case.
Sorry to interrupt again.
Yeah, no worries.
But, so in this case here, the interaction is mediated by photons, no?
By a vector mediator.
Oh, by a heavy vector mediator. So okay, it's not mediated by photons, because I thought you have some millicharge. You say you have millicharged dark matter.
Oh.
So I'm expecting that the interaction is mediated by good old ordinary photons. No?
Yeah, sorry, I guess it's not a very good use of terminology here. Yeah, what it means is really coupling. So I'm imagining a dark photon mediator that can be heavy or light, although in the plots I will show you the light mediator case.
Oh, okay. No, then I'm fine.
Yeah.
Okay, it's not
in many cases,
mediated by the photon.
Right, not exactly, but I guess it would be, I mean, for many calculations, it wouldn't be different from just the true Miller charge case.
Well, it's just that you would have to understand the propagation of the photon through your material, right? I mean, that would presumably be, whereas here, this vector particle, this dark photon is effectively going right through your material. So you can just use, right? That was
there's also screening in this case. I mean, it's just a matter of how this is included, right? So here, that's what the effective coupling is including. There is a screening.
So there is screening, and you're including.
There is screening, yeah.
Okay. Is that where the mass comes from also? The MV is material dependent or no?
Oh, MV is not, I believe, because I mean, once you do the diagonalization, it will still be, so, okay, I guess there are different ways of doing this calculation if you work with different bases. So I guess the least confusing way would be to first diagonalize the mass matrix. And then you will see that there is only the contribution from this mostly dark state that's contributing, but the effective coupling is different from the bare coupling.
Okay, but I wouldn't call that screening. I would just call that diagonalizing the Hamiltonian.
Yeah.
Okay, all right. I think I understand. Thank you.
Okay, cool, thanks. Yeah, for the other two models, we have worked out the operators, and we just, again, circle the terms in this equation. We see that in addition to the coupling to N, we also have couplings to S and L. So these can excite magnons. And again, one of the models is higher order in the power counting than the other. And if we go from the first two to the last two, there's a suppression Q squared. So all this power counting stuff is going into the reach plot. So here I'm showing the projected reach for kilogram year exposure, assuming a background free experiment, basically 3 events per kilogram year, just in order to compare with previous calculations. So because these models are successively higher order in Q, we see that the reach gets successively weaker. Of course, the spin independent model has the best reach, and then the electric dipole model is one higher power, so it gets weaker, and the same for the other two models. And we can parametrically understand the rates. You see that the couplings involve the various quantities that are expected, such as the ionic charges, the dielectric, which contributes to, well, what we call screening, and then the masses of the ions and phonon frequency. For the targets, we consider gallium arsenide and silicon dioxide, also known as alpha quartz. So these have highly complementary features. Gallium arsenide has a relatively simple and symmetric crystal structure, and there are just 2 ions per primitive cell. So that means we have 6 phonon branches. Remember, each ion can move in 3 directions. So this is the dispersion relation in momentum space. So here, these letters label the points, the high symmetry points in momentum space. So we see that the highest phonon energies are around 35 millieV. And for quartz, the crystal structure is a little bit complicated. There are, in fact, 9 ions per primitive cell, so there are 27 phonon branches. And it's also less symmetric than gallium arsenide. And the phonon energies go up to about 150 millieV. So these are quite different.
Can I ask a stupid question?
Yeah.
What's going on in the gallium arsenide? So in the quartz, there's a tetrahedron around each silicon, right?
Mm-hmm.
That, how many, what shape, I can't tell what shape is around the, what's in the center of those things and how many corners are there?
It seems similar to this case, although I guess it's the question of how the
so those are tetrahedrons.
Yeah, how these tetrahedrons come together, right? How these are connected.
So, but it's built out of tetrahedrons.
Yeah, so that just means the crystal environment for each ion
right.
is similar.
Right, and what's at the center of the tetrahedron? Is it the gallium or the arsenide?
I'm not sure, although the crystal environments should be the same for gallium and arsenic. I'm not totally sure on that, but that's my best guess. I mean,
it's just one gallium and the other is arsenide, right? You don't know whether red one is or which one is which.
Yeah, so I thought it should be symmetric under the exchange of the two, although I'm not exactly sure. I mean, it's just because the picture is drawn this way that it seems the yellow ones and the dark red ones are different, but they're likely the same.
So you're telling me that's some base-centered cubic, or?
So, okay, I can't recall exactly.
Okay, it doesn't
it's
matter.
One of those, yeah, it's one of those common structures. Cool. So in terms of experiments, gallium arsenide is one of the targets used in the SPICE experiment, which is part of the Tesseract project that is currently in R&D that I mentioned earlier in this talk. Quartz has not been used in an experiment, but this is one material that we are proposing because we found it to have optimal sensitivity in our theoretical study. And indeed, we see the quartz outperforms gallium arsenide for all of these models.
How do you read out phonons?
Good. So in the Tesseract or SPICE experiment, they're designing very sensitive transition edge sensors. Basically, these are like ultra low threshold calorimeters. You're reading out the basically the cascade decay of a gapped phonon. So I guess, yeah, you're reading out heat.
Okay, thanks.
So one thing to emphasize that these targets do not have S or L order, which means that the coupling, so phonon excitations proceed only via the coupling to the particle numbers. But of course, two of the models also generate couplings to S and L, and we want to probe these couplings as well. And for these, we should better look into magnons. And so in these plots, I'm zooming in on the parameter space relevant for these two models. The red and blue curves are the same as what you saw on the previous slide. And overlaid are the ridge curves from some targets via magnon excitations. So first of all, we look at YIG, yttrium iron garnet, which is a very well-studied ferromagnetic material. So it's described by a Heisenberg model involving the spins of the electrons, but not the orbital angular momentum. And this is the target that's used in the quarks experiment for axion detection. So people know how to synthesize YIG in good quality. And for the other target, we entertain the possibility of using a more novel material called alpha ruthenium trichloride. So this is one of the key type materials that has been studied quite intensively in the recent condensed matter community. So the interesting thing about this material is that there's a honeycomb lattice and the couplings are bond directional, meaning that, so basically these bonds are shown in 3 different colors. Along a red bond, for example, it's only the X component of the spins, of the effective ionic spins that couple to each other. And similarly for the Y and Z bonds. So this very special type of couplings, in fact, have many interesting implications for various questions in condensed matter physics, such as thin liquid and novel phases. But for our purpose, we're actually taking advantage of some different aspects of this material. One is that this has the magnetic order, which is anti-ferromagnetic, involves not only S, but also L, which means that we can also probe the dark matter couplings to the orbital angular momentum. And also, there are some magnon modes at very low energies, below about 10 millieV, and that explains why we can reach much lighter dark matter masses in this material. But of course, since this is highly speculative, we're only using this as a benchmark for showing if we can find a material with these features, we would expect a very similar reach as this one. So again, we can understand the results parametrically, and I'll skip the details in the interest of time. In the end, we find that the magnon reach is parametrically better, but of course, just from these plots, we see that quartz is not too far behind, and quartz is the optimal phonon target. So this is actually encouraging news from the experimental point of view, because detecting phonons is much easier, or at least technically much more mature than detecting single magnons.
In your reach curve, there are some they are not completely smooth. There are some features.
Yeah.
What do they correspond to? Is there some
good? So
to understand?
Yeah, so the features usually come from the fact that different modes are contributing. For example, this one, there's a feature over here, and this is that 1 MeV is basically where the momentum transfer becomes comparable to the inverse lattice spacing. So that's where the modes beyond the first Brownian zone, or the so-called womb clock processes, will start to contribute. And that explains this feature over here. So here is just that there are more modes contributing. They're multiplying by a factor of, I guess, 20 in this case, just because there are more modes. And for the other ones, I guess here there is a transition between acoustic and optical phonons that have very different features. Or I guess generically, because it's a log-log plot, whenever you have the sum of 2 functions that peak at different places, you get a kink or a feature.
So can I ask, I mean, these are pretty complicated materials. So how accurate is the theoretical description of these phonon and magnon modes that you're using? Can you directly test these models or experimentally, or how accurate are they?
Yeah, so I guess there are several parts of this question. One is how accurately are we able to characterize these materials? Like, what's the accuracy of these DFT calculations, right? So I think the accuracy there is pretty good. At least that's what we heard from our condensed matter collaborators. And for some of the materials, they're able to calibrate their calculation against experimental data. But of course, it really depends on how easy it is to perform measurements on a material. So the error bars could vary between material to material. That's one part. And the other part is the dark matter related stuff. I mean, there's the well-known uncertainty related to the phase space distribution of dark matter. Like, what's the local dark matter distribution? What's the I mean, if you use a different escape velocity, the results will look
Yeah,
a bit different.
I know about. I just meant the first thing. So.
Oh, okay, I see.
Thank you. Yeah.
Yeah, I guess for something like gallium arsenide, the calculation we expect to be pretty accurate. But for something like alpha ruthenium trichloride, I mean, we don't even know the exact model for the effective spin Hamiltonian. I mean, there is a literature trying to like take experimental data and DFT calculations and combine everything. And people have written down different models for these materials. So there could be some uncertainty there. All right, so let me conclude, and then we'll have time to discuss more questions. So take-home messages. First, collective excitations such as phonons and magnons offer a promising path to detect light dark matter. On the experimental side, the good news is that new experiments are moving forward. SPICE, which is based in Berkeley Lab, is currently in active R&D, and it will have broad discovery potential over the dark matter theory space. And on the theory side, we have the tools ready based on effective field theories for computing the rates for general dark matter models. And to recap, the theoretical framework consists of 3 steps: matching onto a nonrelativistic EFT, matching onto crystal responses, and then computing the phonon and magnon excitation rates numerically. So I'll end here. Thanks a lot for your attention. Thanks for all the questions. I'll stay around for more discussion.
So let's unmute and thank Kevin for a nice talk. Yeah, questions by somebody other than me.
Or me.
Your reaches are assumed to be background free. Is that your curve?
Yeah.
How realistic is that?
So I guess one irreducible background would be neutrinos. I mean, that that is well known, but there are other detector related stuff that really depends on how good, how well they can make their TES detectors, for example. And that's the part that has a question mark on it. So we're not quite certain, but.
Do you just detect one phonon something, or what's the, when you say the reach?
Yeah, so we're assuming 3 events per kilogram year.
3 phonons.
Yeah. I mean, each event is a single phonon as a primary process.
You keep it at a low temperature or something so that there's no.
Yeah,
thermal.
it has to be it has to be very low temperature, so you don't get thermal noise. The initial state is really the ground state.
So you can really detect, these these EV or whatever they are, a single photon with an energy of an EV. These edge sensors can detect.
So right now, I guess the state of the art is around EV or slightly below, but they're trying to achieve much lower energy resolution. For example, order 100 milli EV in the near future, and even lower in the more farther future. I mean, for these projections, we're being very aggressive by assuming like 1 milli EV thresholds. These are like more futuristic, but people are making progress toward that.
So I mean, I guess, so just to sort of set the scale, EV is not so different from room temperature, right? I mean, a typical room temperature fluctuation is what? Around an EV, or isn't it? If I'm remembering right?
Room temperature is 10 to the minus 3 EV.
10 to the minus 3, okay. So you got to get well below, to get an EV, you've got to, so EV is above room temperature. So it's not a question of cooling, presumably, as much as just backgrounds. Is that true?
So these are athermal phonons, right?
Sure, but thermal noise is, sure, but thermal noise is a problem, right? But if you're telling me the individual phonon energies are far above the thermal temperature, I mean, it seems kind of hard to believe, but it seems like then you shouldn't worry as much about temperature. Is that true, or?
The conversion, right? The room temperature
is it really 10 to the minus 3 EV? Is that really right? God, I remember it's not that. It's not that.
It's a 40th, sorry.
Huh?
40th of an EV.
Okay, but it's around an EV. I mean, it's a 10th of an EV. Huh. All right. Anybody else? Questions?
Oh, maybe I can ask a quick question. In your categorize all the independent operator, it seems that you're working in the momentum space. Is it more easier to working with this spatial space? Why people tend to work in the momentum space? Like the operator is written in terms of momentum space instead of position space. Is there any particular reason for people to do that? Because in the relativistic quantum field theory, we write the effective operator usually in the position space. We're not writing the effective operator in the momentum space. But here you write all the operator in the momentum space, right? So
I mean, you can write it equivalently in position space.
Yeah.
I mean, these are really operators. So, for example, I mean, these are just gradients. But once you get to the Q and V perp, these will be like combinations of gradient operators acting to the left and to the right. I mean, you can do it that way, but in the end, if we're still using momentum space Feynman rules,
okay, sure.
It's just easier to write it this way.
That's true. Okay, thank you.
Any other questions? Well, I suggest we thank our speaker again, turn off the recording, and we can continue the discussion offline. So thanks very much, Kevin.
Yeah, thanks everyone.